Today we're diving into the world of Karnaugh Maps, a powerful tool used in digital logic design. If you've ever wondered how engineers simplify complex logical expressions, the Karnaugh Map, often called K-map, is the answer. It's a visual method that helps us minimize Boolean functions, making circuits more efficient and easier to implement. Whether you're a student or a professional, understanding K-maps can save you time and effort in designing logical systems. Let's start by exploring what a Karnaugh map is and why it's so valuable in the field of electronics and computer science. Karnaugh map is a graphical representation of truth tables. Instead of listing out all possible combinations in a table, the K-map arranges them in a grid, making patterns and simplifications much easier to spot. Each cell in the map corresponds to a possible combination of input variables, and the value inside the cell represents the output for that combination. This visual approach helps us quickly identify groups of ones or zeros, which can then be combined to simplify logic expressions. The K-map is especially useful for functions with up to 4 or 5 variables. Karnaugh Map was introduced by Maurice Karnaugh in 1953 as an improvement over the Veitch diagram. Its main purpose was to provide a more systematic and visual way to simplify Boolean algebra expressions. For K-maps, simplification was often done algebraically, which could be tedious and error-prone. The K-map's grid layout and grouping rules made the process much more intuitive, paving the way for more efficient digital circuit design. Today, K-maps are a standard tool in electronics and computer engineering courses around the world. Karnaugh maps are favored because they make logic simplification straightforward and visual. Instead of manipulating equations, you simply look for patterns and groupings in the map. This reduces the risk of mistakes and speeds up the process. K-maps are particularly handy when dealing with circuits that need to be as simple and cost-effective as possible, such as in embedded systems or hardware design. By minimizing the number of logic gates, you also reduce power consumption and increase reliability. Basic Karnaugh map consists of a grid where each cell represents a unique combination of input variables. For 2 variables, the map is a 2x2 grid. For 3 variables, it's a 2x4 grid, and for 4 variables, it's a 4x4 grid. The arrangement of variables follows gray code, ensuring that only one variable changes between adjacent cells. This structure is crucial for identifying groups and simplifying expressions accurately. The simplicity of the grid makes it easy to visualize and manipulate logic functions. Gray code is used in Karnaugh maps to ensure that only one variable changes between adjacent cells. This is important because it allows us to group adjacent cells that differ by just one variable, which is the key to simplifying Boolean expressions. For example, in a 2-variable K-map, the rows and columns are labeled 0 and 1. In a 3-variable map, the sequence might be 0, 1, 11, 10. This unique arrangement makes grouping possible and effective. Use a Karnaugh map. You first fill in the grid with the output values from your truth table. Each cell corresponds to a specific combination of input variables. If the output is 1 for that combination, you place a 1 in the cell, otherwise you place a 0. This step is essential because it sets up the map for the grouping and simplification process. Accuracy here ensures that your final simplified expression will be correct. Once the K-map is filled, the next step is to group the ones. Groups must be rectangular and contain 1, 2, 4, 8 or any power of 2 cells. The goal is to make the largest possible groups, as this leads to the simplest expression. Each group represents a simplified product term in the final Boolean equation. Overlapping groups are allowed and sometimes necessary for optimal simplification. After grouping, you write a simplified Boolean expression for each group. The variables that remain constant within a group form the product term. By combining all these terms, you get the minimized Boolean function. This process reduces the number of gates needed in a digital circuit, making it more efficient. The visual nature of the K-map makes it easy to spot these simplifications even for complex functions. Let's look at a simple example. Suppose you have a function with 2 variables, a and b. The K-map is a 2x2 grid. You fill in the cells based on the truth table. Next, you group the ones, which might be single cells or pairs. Finally, you write the simplified expression. This hands-on approach helps you understand the power and efficiency of Karnaugh maps in real-world logic design. 3 variables, the K-map expands to 2x4 grid. Each cell represents a unique combination of A, B, and C. After filling in the map with output values, you look for groups of ones that can be combined. The process is the same as before, but with more possibilities for grouping. This example shows how K-maps scale with more variables while still keeping the simplification process manageable. 4-variable K-map uses a 4x4 grid, representing all possible combinations of 4 input variables. This larger map allows for more complex functions to be simplified visually. The grouping rules remain the same, but the increased size means you can form larger groups, leading to even simpler expressions. This is especially useful in designing more advanced digital circuits. Sometimes, certain input combinations are irrelevant to the function's output. These are called don't care conditions and are marked with an X in the K-map. You can use these cells to your advantage when grouping, as they can be treated as either 1 or 0 to help form larger groups. This flexibility can lead to even simpler Boolean expressions. Prime implicants are the largest possible groups of ones in a K-map. They represent the essential building blocks of the simplified Boolean expression. Identifying all prime implicants is a key step in the minimization process. Some prime implicants are essential, meaning they cover output values that no other group does. These must be included in the final expression. Essential prime implicants are those that cover at least one output value not covered by any other group. These are crucial for the final simplified expression. After identifying all prime implicants, you must select the essential ones first, then add any additional groups needed to cover all ones in the K-map. This ensures your solution is both complete and minimal. Overlapping groups in a K-map are allowed and sometimes necessary to achieve the simplest expression. By overlapping, you can ensure that all ones are covered with the fewest possible groups. This technique is especially useful when dealing with don't care conditions or when multiple groups share common cells. The goal is always to minimize the final Boolean function. Karnaugh maps offer a visual alternative to algebraic simplification. While algebraic methods rely on Boolean laws and can become complex with many variables, K-maps make the process more intuitive. By grouping ones visually, you can often spot simplifications that would be hard to find algebraically. This makes K-maps a preferred tool for both learning and practical circuit design. While Karnaugh maps are powerful, they do have limitations. They become unwieldy with more than 4 or 5 variables as the grid size grows exponentially. For very large functions, other methods like the Quine-McCluskey algorithm or computer-aided tools are more practical. However, for most practical applications, especially in education and small-scale design, K-maps remain invaluable. Karnaugh maps are widely used in digital circuit design to minimize the number of logic gates required. By simplifying Boolean expressions, engineers can create circuits that are faster, use less power, and cost less to produce. K-maps are especially useful in designing combinational logic circuits, such as adders, multiplexers, and encoders. Karnaugh maps are a staple in electronics and computer science education. They help students develop a deep understanding of logic simplification and circuit design. The visual nature of K-maps makes them an excellent teaching tool, allowing learners to see the effects of grouping and simplification firsthand. Many textbooks and courses include K-map exercises to build foundational skills. With the rise of computer-aided design, many software tools now include Karnaugh map functionality. These tools can automatically generate K-maps from truth tables and suggest optimal groupings. While manual K-map skills are still important, these tools make it easier to handle larger functions and verify solutions quickly. Karnaugh maps use standard notation and symbols to represent variables and outputs. Rows and columns are labeled with variable combinations, and cells are filled with 1, 0, or X for don't care. Understanding this notation is essential for reading and constructing K-maps accurately. Consistent labeling ensures that everyone interprets the map in the same way. Karnaugh maps can be used to simplify both sum of products (SOP) and product of sums (POS) forms. For SOP you group ones, for POS you group zeros. The process is similar, but the interpretation of groups changes. This flexibility makes K-maps a versatile tool for different types of logic simplification. See how K-maps are used in practice. In designing a simple adder circuit, you can use a K-map to minimize the logic for the sum and carry outputs. By grouping ones in the map, you derive the simplest Boolean expressions which translate directly into fewer gates in the physical circuit. This approach is common in digital electronics design. Multiplexers are another common digital component where K-maps shine. By mapping the selection logic onto a K-map, you can quickly find the minimal logic required for the select lines. This not only saves hardware but also improves the speed and reliability of the multiplexer circuit. Encoders convert information from one format to another, and K-maps help minimize the logic needed for this conversion. By simplifying the output logic using a K-map, you can design encoders that are both efficient and reliable. This is especially important in communication and data processing systems. Karnaugh maps are also used in designing error detection and correction circuits. By simplifying the logic for parity bits or error-checking functions, you can create circuits that quickly identify and correct errors in data transmission. This application is vital in communication systems and computer memory. State machines are used to control sequences in digital systems. K-maps help minimize the logic for state transitions and outputs, making the overall design more efficient. By simplifying the logic, you reduce the number of gates and improve the speed of the state machine, which is crucial in real-time applications. Programmable logic devices (PLDs) like FPGAs and CPLDs benefit from logic minimization using K-maps. By simplifying the logic before programming the device, you make better use of available resources and improve performance. K-maps are often used in the design phase to ensure optimal logic implementation. In memory systems, address decoding logic can be simplified using K-maps. By minimizing the logic required to select memory locations, you can design faster and more reliable memory circuits. This is especially important in microcontrollers and embedded systems where efficiency is key. Control logic in digital systems often involves multiple inputs and outputs. K-maps help simplify the logic for control signals, reducing the complexity of the control unit. This leads to more reliable and maintainable systems, especially in industrial and automation applications. Sequential circuits, which depend on both current inputs and previous states, can also benefit from K-map simplification. By minimizing the logic for flip-flop inputs and outputs, you can design more efficient sequential systems. This is crucial in applications like counters, registers, and timers. Timing circuits, such as those used in clocks and timers, require precise logic. K-maps help minimize the logic for timing signals, ensuring accurate and stable operation. This is especially important in applications where timing accuracy is critical, such as communication and control systems. Alarm systems often use logic circuits to detect specific conditions. K-maps can simplify the logic needed to trigger alarms, making the system more reliable and easier to maintain. By minimizing the logic, you also reduce the risk of false alarms and improve response time. In digital voting systems, logic circuits determine the outcome based on multiple inputs. K-maps help simplify the decision logic, ensuring accurate and fair results. This application is important in both electronic voting machines and automated decision-making systems. Traffic light controllers use logic circuits to manage light sequences. K-maps can simplify the logic for controlling the lights based on sensor inputs and timing. This leads to more efficient traffic flow and safer intersections, especially in busy urban areas. Elevator controllers rely on logic circuits to manage floor selection and movement. K-maps help minimize the logic needed for these decisions, resulting in smoother operation and reduced hardware complexity. This is particularly valuable in modern high-rise buildings. Home automation systems use logic circuits to control lighting, heating, and security. K-maps can simplify the logic for these controls, making the system more efficient and easier to expand. This leads to smarter homes with more reliable automation features. In industrial automation, logic circuits control machinery and processes. K-maps help minimize the logic for control signals, improving efficiency and reducing downtime. This is essential for maintaining high productivity and safety standards in manufacturing environments. Robotics systems use logic circuits for movement, sensing, and decision-making. K-maps can simplify the logic for these functions, leading to more responsive and reliable robots. This is particularly important in applications like autonomous vehicles and industrial robots. Security systems rely on logic circuits to detect breaches and trigger alarms. K-maps help minimize the logic for these detection circuits, making the system more robust and less prone to false alarms. This leads to safer environments in homes, offices, and public spaces. Medical devices often use logic circuits for monitoring and control. K-maps can simplify the logic for these functions, improving reliability and safety. This is especially important in life-critical applications like patient monitors and infusion pumps. Automotive electronics use logic circuits for functions like engine control, safety systems, and infotainment. K-maps help minimize the logic for these systems, leading to more efficient and reliable vehicles. This is crucial for meeting modern safety and performance standards. Communication systems use logic circuits for encoding, decoding, and error correction. K-maps can simplify the logic for these functions, improving data integrity and transmission speed. This is vital in applications like networking, wireless communication, and satellite systems. Summary: Karnaugh Maps are a fundamental tool for simplifying Boolean expressions and designing efficient digital circuits. Their visual approach makes logic minimization accessible and intuitive, whether you're working on small educational projects or complex industrial systems. While K-maps have their limitations, their benefits in clarity, efficiency, and reliability make them indispensable in electronics and computer engineering. Mastering K-maps opens the door to smarter, more effective circuit design.